Welcome to Spring LIB.
In this exercise, we're going to use the concepts of circular motion and friction force. So before solving the problem, I'm first going to give a brief review of these concepts. So let's start with circular motion. Remember that the centripetal acceleration that's associated with circular motion is equal to v squared divided by r, where v is the speed of the particle and r is the radius of the orbit. The acceleration points towards the center of the circle that composes the orbit. And what we need to know about friction force is that there are two types of friction force. We have the static friction and the kinetic friction. The static friction happens when a particle is not moving relative to the surface upon which it lies, and the friction force varies from 0 to a maximum value that is equal to the coefficient of static friction, μs, times the normal force that the surface exerts on the body. The kinetic friction, on the other hand, has a force that is equal to the coefficient of kinetic friction, μk, times the normal force. And with these informations, we can go on to our problem. So what we have is a spool represented by the letter S that's attached to this inclined rod shown here in the picture. And the distance between point A and the spool S is 0.25 meters. The mass of the spool is 2 kilograms, while the static friction coefficient between the spool and the rod is 0.2. The spool is free to move along the rod. And our goal is to find what is the minimum speed, the minimum constant speed, v, that the spool can have when making a circular orbit, as shown here in green, so that the spool does not slip down the rod. Okay, so in order to solve the exercise, what we need is to draw a force diagram on the spool. Okay, so this here is the spool. The forces that act are the normal force perpendicular to the rod. Then we have the gravitational force. And since we want the spool not to slip downwards, then the friction force must be pointing in the other direction. And these are the forces that act on the spool. Now, I'm gonna define this angle theta here. Okay, notice that this angle here must also be theta. And I'm gonna decompose these forces into an x component and a y component, such that the y coordinate points downwards, points upwards, and the x component points to the left. So in the y component, we have n times the sine of theta minus or plus the friction force times the cosine of theta. Actually, I'm sorry. N should be the y component of that n is actually n times cosine of theta. I'm sorry for that. And the y component of the friction force is Fy times Ff times the sine of theta. Sorry for the confusion. And then we have minus mg, and this is equal to 0. In the x component, we have n times the sine of theta minus the frictional force times cosine of theta, and this is equal to, according to Newton's second law, the mass times the acceleration. Now we know that the acceleration is v squared over r, since the spool is moving in a circular motion. Okay, and the circular motion is around the y-axis. Okay, so what we need to do now, first of all, is to notice that if we're looking for the the smallest value of v, then we're actually looking for the greatest value of the frictional force. And we know that the greatest value that the friction force can have, so that the spool does not slip down the rod, is equal to the coefficient of static friction times the normal force. So I'm gonna substitute this into our equations. First, I'm gonna substitute it into the equation for the y-coordinate. So we have n times cosine of theta plus mu s and sine of theta is equal to mg. And I'm going to isolate n, so we have that n is equal to mg divided by cosine of theta plus mu s sine of theta. So this is the value of the normal force when the friction force is maximum. And now I can find what is the value of v that corresponds to this normal force. So I'm going to take the equation for the x-coordinate. We have an n, which I'm going to write as mg, divided by cosine of theta plus mu s sine of theta, plus the frictional force, which is mu s times n, cosine of theta plus mu s sine of theta. And actually, the first n, this one here, should have a sine multiplying it, and the second one must have a cosine multiplying it, and there's a minus sign here. So notice that now this is in accordance to the equation for the x-coordinate, and this is equal to mv squared over 2. So this is just n times sine of theta minus the frictional force, which is mu s times n, times cosine of theta, and this is mv squared over 2. So the m's cancel out, and we have 2. Actually, this shouldn't be 2, this should be r. So we have r times g times sine of theta minus mu s cosine of theta divided by cosine of theta plus mu s sine of theta and this is equal to v squared. So I'm going to just take the square root on the left hand side, and now we can substitute the numbers. Okay, but in order to substitute the numbers, before I do that, we need to realize some things in the drawing. First, according to the exercise, the triangle, this triangle here, that is formed by the rod and the x coordinate is similar to a triangle that has a hypotenuse 5 and legs that are equal to 3 and 4. This means that theta here is such that the sine of theta is 3/5, while the cosine of theta is 4/5. Okay, and the radius of the orbit is actually just this distance here. Okay, and this distance, r, is equal to 0.25 times the cosine of theta. Okay, this here is theta. So it's 0.25 times 4/5, and that it is 0.2 meters. So that's the radius. So we have that v is equal to the square root of 0.2 meters times 9.8 meters per second squared times the sine of theta, which is 3/5, minus 0.2 times 4/5 divided by the cosine of theta, that's 4/5, plus 0.2 times 3/5. So V is equal to 0.97 meters per second. And this concludes our exercise. This is the minimum speed that the spool can rotate.